Good afternoon, everyone. This is Ernie Parker, and I've got a short webinar of only about 11 slides here, talking about some things that are in your Lightning reference that will be handy for you, and they are identifying pump mounts and when to use a case drain. So taking a look at the first slide here, I'm going to expand this and then move around a little bit. And if you would take a look in your Lightning reference, you will see this. And let me back up just a second. If you look at the bottom of the screen, you'll see a page number. I guess this one doesn't show up that well. I'm going to give you the page number here that you can follow along with me as we look at these mounts. One of the things that's really handy for us in the fluid power industry is some uniformity. And what I mean by that is, how can I find a pump that is a standard mount? We're on page 88 right now. If you'll follow me in the Lightning reference, where can I find a standard mount? And if I order these components and I have to wait a month or two for them to come in, how can I start building my bracketry that I want to mount this pump to? Well, this is a solution for you. So as we look on page 86 of your Lightning reference, you will notice that we have a diagram right here. And this is a typical SAE mount for a pump or a hydraulic motor. And the one I'm going to talk about today is what we call the SAE A mount, Society of Automotive Engineers, and this is called an A mount, a 2-bolt A mount. Every manufacturer of a pump that makes one that they advertise as an SAE A mount will have these two mounting holes over here, will be 4 3/16 inch apart. There's a pilot right here. This pilot, if we go over to the left side here, you'll see it stick out just a little bit. And that pilot has a diameter of this dimension, which is 3 1/4 inches. I'm going to go to the next slide here and just show you what we're talking about. And again, I'm going to blow it up as big as I can. And here's the one. I'm on the second column here is an A mount. That A noted, here's that 3 1/4 inch pilot. So if you drill a hole in a piece of metal with a hole saw, that's 3 1/4 inches, this pump will slide right into it. And then if we go over to the K dimension, these are the two mounting holes. They're 4 3/16 inches apart. So what I'm suggesting you do is that you go back, whoops, sorry about that. You take this unit right here and draw that up on one of your CAD programs to scale. If you use AutoCAD or any of them, you can print it out to scale. You can draw that up and make yourself a perfect pattern. And then you can take a punch and you know exactly where to mount these two holes or drill them. So all the dimensions are here for that, how big they should be, and that'll take the torque of this particular motor or pump by going with that diameter bolt. Okay, going back to this, here's some other things that we can see about that. I'm looking again at the A mount. It has a straight shaft. And you see this dimension right here? This is the diameter of the shaft, 0.625. So every SAE A mount will have a, if it's truly an A mount, will have a 5/8 inch shaft. Does that mean I can't get a pump or a motor with the same mounting but have a larger shaft, like a 3/4 inch or 7/8? Yes, you can. But then they can't advertise it as an SAE A pump. They can advertise it as an SAE A mount, but not as a pump, because the shaft is different than the standard. An AA mount, which is a little confusing, is actually a smaller pump, but a B is larger. Wouldn't that confuse you a little bit? Now BB, the difference between a BB and a B is everything's the same except the shaft has been boosted from 7/8 of an inch to 1 inch to allow more torque. This is usually typically applied on skid steer loaders like Bobcats, where they have a double hydrostatic transmission to run the wheels on each side, and then a piggyback that runs the loader. And if they're going to put a bigger pump on there to get higher flow, eventually the shaft is too weak to handle it. So they've offered a BB mount where the shaft is greater than the B. They have a C mount and a CC and a D and an E, etc. You're probably only concerned with the A mount. I think that's the pump that you're getting. If, by the way, you wanted to mount this inside another pump, you'd probably go to a spline shaft. And every A mount has a 9-2 spline here. There's your spline shaft, which is standard again for these components. So there's nothing magical about it. It's just a fact that these are standards for our industry. Years and years ago, back in the 50s and 60s, when companies like Cincinnati Millicran, et cetera, were building machines for the automotive industry, there would be some mom and pop shop that would build them a pump and put on the machine. Well, if the pump wore out, and especially in those days when they had this lousy filtration and everything, they didn't have the means to make a super duper pump to start with, that these companies would go out of business, and now you've got an expensive machine that you can't get parts for. So the automotive industry insisted on standardizing these components. And even if you buy a Rexroth from Germany, if it's an SAE A mount, it will fit in to the standards. Okay, I'm going to shift here to tubing. Some of you have been asking me about, can you plumb with hard tubing? Yes, you can. And I just want to give you a little bit of information as to line size. I'm going to cover both tubing and hoses before I get to the case drain. When you're working with a pump, the suction of a pump should have a velocity of under 5 feet a second. Some manufacturers say 4 feet. Some say 5. It varies a little bit. The NFPA standard was 5 feet a second. And I like this particular one for a number of reasons. And if you have good, proper plumbing, it works great. Do not put an elbow right at the inlet of your pump if you can help it. You can put a sweeping elbow like on the end of a hose, kind of a nice sweeping 90-degree fitting on the end of a hose is just fine. But try not to put an elbow right into the inlet of the pumper. Imagine the oil coming in 5 feet a second and hitting a brick wall and having to make a 90-degree turn at 5 feet a second. It's really hard to get that oil in there. And your oil is going to be fairly cool at room temperature. We consider that cool. Our normal running temperatures are 120 to 140 degrees. So the oil is going to be a little stiff. And if you're going to try and get in that pump at 5 feet a second, you're going to end up struggling with it, kind of like sucking a cold malt in a little straw. It doesn't work real well. But if you go down the chart here, you can go down, if you know how many gallons per minute you're pumping, and let's say that we're looking at something like, here's a 2.2 gallon per minute system. We're going to have 0.59 PSI drop per foot in that suction line. And if you follow all the way back over to here, you'll see that that's a 1/2 inch OD tubing with a 35 thousandths wall. These wall thicknesses are standard sizes. I would stay away from 28 thousandths because when you try to bend it, it kinks. But 35 thousandths is good for low pressure and medium pressure in smaller diameters. 49 is a little thicker wall, 65, 83, etc. The wall thickness, the reason for that is to handle the higher pressures, which we'll talk about in a little bit. But also, the outside of the tubing is always the same. If you go to 3/8 inch here, 1/2 inch here, you notice they're all the same. It's just the ID of the tubing gets smaller. So tubing is measured by the OD. Okay, now I'm going to the next slide. This is for suction velocities. Now let's look at this one here. go to the next pitch slide. Come on. Here we go. Now this slide again, if you're watching in the lightning reference, you will see the page at the bottom. I should have showed you that before I blew it up here. 113, 112, 113 are the two pages I'm working on. The maximum velocity that I'd like to see is 20 feet per second. You can go slower. There's nothing wrong with that at all. But going faster, and you can kind of see these squiggly lines here, everything to the right of that's turbulent, everything to the left is laminar flow, and in this area is kind of a transitional. So here you can notice going at 20 feet a second, if I take that same 2.2 gallons a minute, here I've got a much smaller size line. In fact, 20 feet per second is 1/2 the diameter of 5 feet per second. Remember, when you double the diameter, it's 4 times the area. So if I can handle a certain amount of flow at 5 feet per second in a given line, if I go 20 feet, I can get by with a flow piece of tubing that's 1/2 that diameter. I just want you to take a note over here. When you make an elbow, I'd ask you to be careful and try not to put an elbow right at the inlet of the pump. Look at here. Now we know in a perfect vacuum, you can pull 14.7 PSI. Pump manufacturers recommend a maximum of 2 to 3 PSI vacuum, which translates to 4 to 6 inches of vacuum. Even though you can pull higher, it's not recommended. Look at right here. If you went through this elbow at this condition, you'd have 16 PSI drop. You can't even suck oil through that because you don't have enough atmospheric pressure to do it. All these would require almost all the way down here a perfect vacuum to get the oil in. So you have to oversize. And as you oversize, then you can get your flow through there. But why not just not use it? Look, when I go straight through a T, there's 5.4 PSI drop compared to 16.4. I make that right turn, 17 here. Here's 23. Yes, this is 30 feet a second, and we're running 20 feet a second, so the numbers will be just a little bit lower, but it really makes a difference. And so what I'm saying is, if you're teeing into a line and you have high flow in one direction, try to go straight through and bring the low flow in the branch. It'll be a little more efficient system. It doesn't cost you a dime more to do it one way or the other. It's just more efficient by doing that. So keep your eyes open as you're plumbing to think of nice laminar flow. The next slide here is on page 124, and this is talking about the pressure ratings of pipe. Excuse me, tubing. We're using tubing, not pipe. Remember, we're not supposed to use black pipe unless we absolutely have to coming out of the reservoir at low pressure. This is hydraulic tubing. A 1/4 inch, we have 3 different tables. We want to use the top one that has a 4-to-1 safety factor. So if I were to ask you what's the maximum pressure I can use on a 35 thousandths 1/4 inch piece of tubing, it's 3,500 PSI here. If I went to 49 thousandths, I can go to 4,900, and 65 thousandths goes up to 6,500, kind of a coincidence there. But if I drop down to 1/2 inch, 35 thousandths is virtually half of the 3,500 here. And you can see the numbers are lower. So there's a chart for you that gives you pressure ratings of tubing. That was page 124. Page 114 and 115, these are ones you're more likely to use. If you're using a hose going to your pump, again, keep your velocities under 5 feet a second. I'll go over in this chart so you can see my arrow here. Now let's say that I'm pumping, here's 6.88 GPM. That's probably a little higher than what you have, but that would take a hose here that is 3/4 inch. These numbers right here, this is the ID of the hose. Now you notice I said ID. Tubing is measured by the outside diameter. Hose is measured by the inside diameter. That makes it a nicer choice. Hose is also used for pumps in the real world for vibration and pressure spikes. So pick out your flow that you're working. Look at 5 feet per second on a suction line, and that's the size hose you need. Now I'm going to go to the next page, 115. And as I blow it up, now when I want 5 gallons a minute, I come down here, or 10 gallons or whatever, I'll pick it up and I can go right to the right and see what size hose. This is an oddball, but here's your 6 gallons a minute. Whoops, 6.88 at 20 feet per second under the GPM column. I'm going to slide over. That now takes 3/8 of a hose instead of 3/4. So your pressure lines can be smaller. If you're at 3 gallons a minute or less, you can use a 1/4 inch hose. The advantage of smaller hoses is you can make sharper turns with it. But remember, this is pressure line, so I'd put an X above this area too. And here you'll have a 7 psi drop per foot in this line. Whereas if I go up to 3/8, look at the difference. From 7, it drops to 3.1 psi drop per foot. That means you're putting in less energy to get the same amount of work done. If I go to a 1/2 inch hose, we're down to 3 psi. So there isn't a lot of difference between the 3/8 and 1/2. Once you get big enough, but the 1/4 inch, for every foot of hose, you're going to have 7 psi drop. So just keep that in mind. Okay. Next page that I want to talk about is some hydraulic hose data. When you order a hose, if you're not getting it from Jeff McCarthy, who's doing the safety for you, and you're buying something off the street from somebody that's reputable, you're probably going to buy either a 100R1 or a 100R2 hose. Those are SAE standards. And again, if I looked at a 1/4 inch, a 100R1, you don't have to worry about the A, the AT, and AB. That's for different types of things. So just the 100R1 is good for 2,750 PSI in a 1/4 inch. So if you're going to 3,000 PSI, you should look for a 100R2 hose, and that's good for 5,000. There's safety factor involved here, yes, but you're not supposed to use it. That's for pressure spikes. So if I see a system where you have a 1/4 inch hose and you're going to 3,000 PSI, I might look at this chart and say, okay, you can only go to 2,750 or going over the rating of that hose. You also have to be under the rating of the component. Let's say you boost up to 3/8 because you want a little less pressure drop. You look up here at the 100R1, which is a single braided hose, is only good for 2,250 PSI, whereas you buy a 100R2, it's good for 4,000 PSI. Now you're in your safe limit if you're deciding to pump up to 3,000. So this is another chart you need to use. If after looking at this page, and you say, well, what do those numbers mean? If you go to page 130, excuse me, the pages before 126, 7, and 8 talk about what those different numbers mean. So it's excellent reading material when you have nothing else to do. There's a lot of good information in here. Okay, is there any questions on that part of it so far? If not, I'm going to move to the last area, which is proper mounting of case drains. And what I have here, and when it's just a couple of pictures, these are ones I wanted to show you this symbol right here. When there's a case drain, you see it's a dotted line going to this little reservoir symbol you put on the side of a pump or motor. If you're using piston components, a piston pump or motor, you most likely need a case drain. On a gear pump, probably not. But if there is a case drain and you're back pressuring both ports, in other words, you bring in a couple thousand PSI to one port, and you might have at one particular case high pressure at the opposite side of it. If you have a situation like that, what happens is it wants to blow the shaft seal out when they're both pressurized. Now, some of these pumps have built-in check valves. Most of the Eaton hydraulic gerotor motors that are used for wheel drives have built-in check valves here. So if this side is high, the oil that leaks past internally gets out to the shaft seals, allowed to drain to the other side. And if the other side's high, it allows you to drain back. Some manufacturers will advertise you can put 2,000 PSI back pressure on a motor without a case drain. And a lot of customers love that. You don't have to hook it up. The problem is, over time, the shaft seal will wear a groove in the shaft of the pump itself. You think, well, it's starting to leak now. I got to replace the seal. You take it apart, and there's a groove there in the shaft, and you have to replace everything. A case drain is a pretty simple solution to that. Now, in some of the piston motors, you'll just flat out blow the seal right out, and you'll be wet. And you think, okay, now where am I going to get another seal? You know how long it took you to get the pump initially. So if you have the option, it's a small port. On this particular one, you see it right here on top. Here's one on the bottom. Right here's a port for that. When mounting a pump or a motor and you have a case drain on it, mount the case drain on the top if possible, or at least on the center line of the shaft. If it's coming out the side and you don't want to rotate the unit, make sure it's at least half full. What that is that's the oil that's floating around inside lubricating this pump. But we don't want to build up pressure. You can blow the pump apart or the motor, or blow the shaft seal out if that's the weak link. So we want to vent that, and we have that oil going through. It's a small amount of oil, and doesn't seem like it's dangerous unless it's totally blocked and you're getting up in the high pressure, and then you've got yourself a little hydrostatic container here full of high pressure oil that can blow up on you. But by mounting on top, you keep everything lubricated. The other thing, if you mount this on the bottom, you can have this case with air in there, and it's going to make noise. A lot of the dampening of the swash plate when you're running with real electric motor or gas engine is dampened with the oil that's inside here. And if you don't have that full and you have air in there, it's going to make a lot of noise. I mounted one system where I could not get the case drain up to the top. It's on my drill press, and it took over 6 months to get the air out of it, of using it, before it quieted down. So center line of the shaft are better if you need it. If the component doesn't need it, leave it off. It's to your advantage not to have to do it. So that's where you use the case drains. And I've seen 1 or 2 applications where I suggested that you put a case drain on because I knew they were back pressuring the component. And if both ports are pressurized, think case drain. Any questions? That's the end of my presentation for today. I hope it helps a little bit. I hope you've had a chance to look at your lightning reference and start to pick up on a few of these things. It'll make your system a little bit better just by knowing the differences. Note, I did not say you cannot use a 90-degree elbow coming out of the pump or going into a motor. I only said to the inlet of the pump is where I don't like to see an elbow. So keep that in mind. I'm not saying you can't use them. You see them all the time. And there's a lot of circuits out there that are not designed properly, but if you look at them and hear them, you'll hear they're making noise and not as efficient as they could be. So, any comments? I think this concludes our presentation today. I thank you very much for taking the time watching this, and I wish you the best in your competition, and don't hesitate to email me or phone me with questions along the way, whether it be on this later or something else that you have a comment about. Thank you very much.